Let's look at this question. Figure 1 shows the net of a square-based pyramid. Okay, you can see here on the figure 1. Cut from a square of cardboard of length 30 cm. It's already marked on the diagram here. The net consists of a square, okay, of sides ACM. Okay, so you can see on that figure 1 as well as in figure 2, the length of this square is ACM, and 4 isosceles triangle, okay, which is 1, 2, 3, 4, which represents the 4 sides of the pyramids. They are all isosceles, so it's a regular pyramid, each with a base of ACM and perpendicular height, okay, of h. Okay, this h, the small h, refers to the height of the isosceles triangle, and that means on one of the faces. So this capital H refers to the height of the pyramid. The net is folded to form a pyramid which has a square base of length ACM, okay, which is marked in the diagram 2, and vertical height capital HCM, which is also marked in the figure 2, are shown in figure 2. Show that capital H is squared, okay, the square of the height of the pyramid is equals to 225 minus 15a. So we know for a fact that it's got to something to do with Pythagoras theorem that we need to use on this. Okay, we will come to that in a while. Let us look at this diagram. Okay, so the height of this isosceles triangle is little h. So small h, and this length is a. And if you look at this, okay, if you add up the h, a, and the h together, it should equal to 30 cm. So let's form the first equation. So in which a plus couple of h, h and a h, so which is 2h, is equals to 30 centimeters. So if you look at what we need to prove, okay, it does not have small h. So I need to make small h the subject of this particular expression, so that I can substitute into the second equation, which I'm going to create in a while. So 2h is equals to a plus 2h is equals to 30. So the small h would be 30 minus a, and then we're going to divide that by 2. 30 minus a over 2 is the value of small h. Now let's calculate what would be the square of h, okay, h squared. So which would be the same as 30 minus a, right, and over 2, the whole thing squared. So that will be the h squared. Now what is the length of this part? Okay, if this whole thing is a, and of course this is smack in the center, so this is half of the length of the square, so this should be here to here should be a over 2, and this is of course was obtained from this isosceles triangle that was folded to create this slant face of the pyramid. So the height here should be the small h. So now you can see there is a right angle triangle inside the pyramid, and we could apply Pythagoras theorem on this. So by Pythagoras theorem, we know that the height squared plus a over 2 squared should be equals to the hypotenuse squared. So in this case, the hypotenuse is the small h. So the h squared, if you make it the subject, it should be equals to the hypotenuse squared minus the square of this particular adjacent length. Okay, so a over 2 squared. Now, so we have already calculated what is h squared here. So let us replace the h squared from what we have formed earlier. So the h squared would be equals to 30 minus a over 2, then the whole thing squared. From that we're going to subtract the a over 2 squared. So h squared should ultimately be equals to, so if I were to, okay, simplify this and write it, this should be equals to 225 minus 15a. So of course you can I have skipped a lot of steps in between. Okay, 30 squared is going to become 900 minus 2 times 30 times a, and then we can do all the kind of manipulation, and ultimately you will be able to prove that from this, since we have already eliminated the small h, it's all in terms of capital H, okay, and small a. So you should be able to manipulate and prove this is equals to 2 to 5 minus 15A. Now find the maximum possible volume of the pyramid. So we need to find what's the volume of this pyramid, and the question says you need not show that this value is indeed a maximum. So in other words, you do not have to go out of your way to find the second derivative and all that. So find the maximum possible volume of the pyramid. So what's the formula for volume of a pyramid? Is 1/3 times the area of base, which is A times A, which is A squared. So that's why we've got A square here, times the height, okay, from the base to the vertex, which is indicated by capital H. Now the capital H, okay, we already have proven in the first part, okay, H squared is equals to 2 to 5 minus 15A. So I can square root this right hand side to make capital H the subject, so as to substitute into the volume function. So this should be equals to A squared over 3, which is this and this, and then the value of the H should be equals to 2 to 5 minus 15A square root, or I can write it as power of half. So of course we have volume as a function of the A, which is the length of the square base. So now let us differentiate, because we want to find what's the maximum possible volume of the pyramid. Of course at dVdA is equals to 0, that's when you're going to get the maximum volume of the pyramid. So dVdA, so we could use product rule. So I'm going to keep the A square over 3 fixed, and then we're going to differentiate this by chain rule. So of course to do that, you're going to bring the half to the front, and then you're going to write 2 to 5 minus 15A to the power of half minus 1, which should give you minus half, right? So from the power you're going to subtract 1, and then minus 15A, if you differentiate what is inside the bracket, that's going to give you a minus 15. So I have kept this fixed and I have differentiated this by product rule. Now I'm going to keep 2 to 5 minus 15A to the power of half fixed and going to differentiate this part. So 2 to 5 minus 15A to the power of half, I'm keeping it fixed. And if you differentiate A squared over 3, so of course you would bring the A to the front and subtract 1 from the power. So that's going to end up giving you 2A to the power of 1 over 3. So there we have dVdA, okay, expressed in terms of A. So of course you could simplify this by doing all kind of manipulations and all that, in view of not having enough space in my presentation. So I have skipped all those steps. So you can pull out a piece of paper and you can just simplify all of this and reduce it to prove it's equals to this. Now that you got this, okay, so what would be dVdA when the volume is maximum? At Vmax, dVdA must be equal to 0. So this is your expression for dVdA. Okay, so denominator certainly cannot be 0, because otherwise dVdA becomes undefined or becomes infinity. So it's either your 75A must be 0, of course, in which case A would become 0. If A becomes a 0, the pyramid does not even exist. So it's either A is equal to 0 or A must be equal to 12, as you can see, right? So 75A times 12 minus A, so the numerator must be equal to 0. If that is the case, we're going to have A equal to 0 or A equal to 12, and of course A cannot be equals to 0, because otherwise the pyramid simply doesn't even exist. So the value of A, okay, should be 12 for the volume of this pyramid to be maximum. Find the maximum possible volume of the pyramid. Now what we have found is what would be the value of A that would make the volume maximum. Now we're going to find the maximum volume itself. So what would be the maximum volume? Vmax is equals to, so this is the formula for volume. Of course this is the part that is in terms of A. So we're going to substitute into this. This is the Vmax, right? So we're going to replace all the A's with a 12. So it's a 12 squared, because A is a 12. So 12 squared divided by 3. And then inside the bracket you've got a 15A, so 15 times 12 to the power of half. And when you evaluate all of this and you simplify, you should get 144 root 5 unit cube, and this should be the maximum possible volume. You do not need to verify whether this is maxima or minima, because the question already says you do not have to do that. So if you do that, you will get 5 marks. Now find the value of A for which this time the total surface area of the four triangular faces of the pyramid is a maximum. Okay, once again you do not need to show that this value is indeed a maximum. So okay, what we have is four of the isosceles triangle. The base of the isosceles triangle is of course A, and the height, just now we remember, if you recall, the height was a small h. So half times base times height, that's the area of one face, right, of the slant faces or the isosceles triangle. And since there are four of them to make up the complete four slant faces, so I'm multiplying it by 4, right? The question says find the value of A for which the total surface area of the four triangular faces only. Okay, it does not include the base, only the four triangular faces, and that's the reason why I did not include the base. So if you cancel the 4 and the 2, you're going to end up getting 2AH. Okay, so that should be the area of the sum of the area of the four triangular faces. So what we are going to do is we're going to substitute the h. Okay, from the first part we already made h, we expressed h in terms of A. So h was, if you recall, is 30 minus A over 2. So if you want to calculate what's the area, so the A, I'm just writing it as A, but the small h I'm replacing it in terms of A. So I get a 30 minus A over 2, and we can cancel the 2 and the 2, and we can just multiply the 30 with the A. So you're going to get 30A minus A squared, okay, as the value of the area, right? Now, but that's not what we want. Okay, we don't want area in terms of A, but what we want is find the value of A for which this area is a maximum. In order to find the maximum, we need to differentiate the A with respect to the small a. So dA is equals to, of course, 30A if you differentiate is going to become 30, and A squared if you differentiate it should become minus 2A here. And at the maximum value of the area, so dA should be equal to 0. So at A max, okay, dA must be equal to 0. So if that's the case, 30 minus 2A must have been equal to 0. And of course you can factorize and pull out a 2, or you could just simply 30 divided by 2, and that should give you A is equals to 15. So the question only wants the value of A, so we can stop here. Okay, you don't have to go and substitute back and find out what is this maximum area itself. So A is equals to 15 is the answer for this. Describe the shape form from the net in this case, right? So substitute the A is equals to 15 is what we got just now into h squared is equals to 2 to 5 minus 15A, which is what we proved in the first part of the question. So if I were to substitute, okay, A equal to 15, right, into this expression, so what am I going to end up getting? 2 to 5 minus 15 times 15, which is of course equal to 0. So when the height here, if this height, okay, becomes 0, so do we in fact have a pyramid, or a pyramid with a height of 0? It's not even a pyramid, right? So it will not be a pyramid, as the pyramid cannot be formed with no height. So that would be the shape of the that will be the shape form from the net when A is equals to 15. So it will not end up becoming a pyramid at all.